Hello, everyone. I'm Jim Kekelius, the head of the School of Physics and Astronomy. I want to welcome you to this colloquium. I'm very thrilled to see the turnout. I discovered recently that there is a Minnesota connection with today's speaker. As a new graduate student at Princeton, he was assigned to work on a problem over the summer with an assistant professor, our very own Professor Ben Bayman, who is here today. Ben, congratulations. Professor Kip Thorne told me that Ben taught him group theory, and it's stuck. If you were at the Misel lecture last night, you saw the 500 seats in McNamara filled with a standing room only. The overflow room of 150 was filled, and we had a wait list of 150 people to attend. So I've decided that from going forward, all public lectures will be given by someone named Kip. With that, I would like to introduce Professor Vuk Mandich, who is a student of Kip's.
Thank you very much, Jim. It is really my pleasure to introduce Kip today. As I was figuring out what to say today, I took a look at his bio sketch, which you can find online. It's very easy. You can Google it. And I found it to be an amazing piece. I would recommend it to everyone to take a look. It's very informational. For example, if you wanted to know what are all the possible awards that you can get in physics, and more broadly, he actually prepared a pretty comprehensive list. You'll find other gems as well. There's his involvement with gravity dates back to his childhood. It's actually an inspirational story. His contributions back in 1970s have laid down the foundation for the field of gravitational waves. He and his students since then have been telling us how to calculate waveforms for different astrophysical and cosmological sources. He's worked with experimentalists to develop the actual technologies that LIGO is using today. He's worked with the NSF and other funding agencies to actually build the support. He built a community around the idea. And all of that took about 4 decades, give or take, and 52 graduate students. For those of us who have advised graduate students, we know what that number means. And it's just unbelievable. Since 2009, I think, he's ventured into a new direction. He's actually made a whole series of interesting contributions to promoting our field to the general public, including paintings and poetry and the movie Interstellar that we'll hear about today. But from a more personal note, yes, I was an undergraduate student, and he was my advisor. This is now 30 years ago. Later, a few years later, I was back at Caltech for a postdoctoral position, and I started with LIGO at that time, and he influenced me in many ways. His advice was invaluable from both personal and professional side. His advice to me when I joined LIGO really helped me figure out which direction I wanted to take, and my first paper was actually on his nudging. But I'll tell you one anecdote. So when I was an undergraduate student, so this is back in 1995 maybe, I would meet with Kip more or less every quarter. They have trimesters, there are quarters. And we would talk about things. And once he told me, you know, all of us have our strengths and weaknesses. And you know, you have to recognize what your weaknesses are, and you have to work on those. You know, focus on those so you can be better at it. So for example, he said, like, if you're a shy person, maybe you don't like working with people, or maybe it's difficult for you to work with people, you should put yourself in a situation where you have to work with people so you get better at it. Of course, I was sitting in his office at that time and thinking to myself, I need another advisor. because I don't know what he's talking about, and it's definitely not helping with my E&M homework or whatever. It took me years to realize that he was talking about me. And many years later, I remember these things, and it's these words come back. And now here I'm working with a collaboration of 1,500 plus people. So it is really a pleasure for me to see him in this room today. It's a remarkable journey that he's gone through, and a lot of advice and wisdom that he has shared with many of us. So without further ado, Kip.
Thank you, Vuk. Can you hear me? So I had a very interesting day today, particularly meeting with Michael and Vuk's LIGO group, which is astoundingly strong and doing really remarkable things. It's just so interesting to be here at the University of Minnesota. Okay, just checking the time, and so I have to get accustomed to how I'm handling this lecture. Okay, I'm talking about the physics of the cult movie Interstellar. I didn't realize it was a cult movie until December 2022 when I drove through Eureka, California. That's a city of about 50,000 people in the northern end of California. It's really rural California. And there is the Arcada Theater. It's one of these old theaters, a grand old theater that they don't really normally show motion pictures in anymore. And in the modern era, but they were trying to get people out over the holidays to at least sell a few tickets to something. And so they had 2 days on which they were having concerts by the funk band, a local funk band, and then 1 day on which they were screening Interstellar. And I figured if Interstellar was in the same class as a local funk band in rural America, there was something sort of cultish about that, and so indeed there is. And then it was only a few months later, maybe less than that, when Steve Chu, whom you may remember was the Secretary of Energy in the first Trump in the first Obama administration, and he phoned me up and he said, "We would like you to give a colloquium, a physics colloquium about the physics of the movie Interstellar." And I said, "That movie is about 8 years old. I mean, what's going on?" And he said, "We want to get the students to come out. And we figured this is the best way to get them to come out. They're not coming to the colloquia anymore. and this will bring them out to the colloquium." And indeed they did. And so you're getting a variant of the colloquium I created for Steve Chu and for Stanford. I found that it was very popular there, and that indeed to talk about the science underlying Interstellar is great fun and also educational. So let me begin by talking about the making of Interstellar. The seeds of Interstellar were laid in September 1980 when my friend Carl Sagan, an astrophysicist who did a lot of stuff in Hollywood as well, called me and said, "Linda Obst wants a blind date with you." Linda Obst was a movie producer who, it turns out, had just moved to Hollywood recently. She'd been a science editor for the New York Times, but she moved to Hollywood and was becoming a movie producer, a very successful one in the end. And she wanted a date outside of Hollywood in order to maintain her sanity, and somehow she picked me. And so we went out together, and I was too nerdy for her, and she was too intense for me, and so the romance went nowhere. But 25 years later, after she had made the movie Contact with Carl Sagan, and I had helped them a little bit with that movie, and Carl had tragically died, she phoned me up and said, "Would you like to brainstorm with me for a movie?" And I thought about it for a few microseconds and then decided, yes, one, it would be fun. Two, how else could I reach a huge audience as a professor? How better to do that than through a movie that might have some really interesting science in it? And so we agreed to do this together, and we wrote a treatment for the movie, conceived the movie, wrote a treatment for it that was called Interstellar. And she brought on Steven Spielberg to direct the movie. And Steven, when we first met with Steven was very enthusiastic about this. He'd never done a movie of this sort with a scientist. I told him I would hope that nothing in the film will violate firmly established laws of physics or our firmly established knowledge of our universe, and that speculations about poorly understood physical laws in the universe will arise from real science. And he said he would buy into that. He would try to make a movie of just that sort. So we were off and running. And they together brought on Jonathan, or Jonah Nolan, who was Christopher Nolan's brother. He had not done any movies except for writing screenplays for his brother at that time. He's been very successful since that time. He came on board to write the screenplay. And he was very talented. He didn't know much science, so I fed him many relevant science books. And he spent a lot of time reading relevant science books of a semi-popular sort. And then he brainstormed with me on the science. And we went through 3 drafts of the screenplay under the oversight of Steven Spielberg. And then on June 8, 2010, Spielberg dropped out. Now, this is not a terribly big surprise. Spielberg carries along several times more movies in the early creative phase than he can possibly make. And then he makes a decision, which ones am I going to actually direct? And what will I discard and let somebody else pick them up? And so he had a choice between Lincoln and Interstellar. And he made the right choice for him. He chose Lincoln. He'd already done science fiction. His heart was not all that deeply into this movie. He was enthusiastic about it, but not at the level that it turned out that Christopher Nolan was. So the movie was stopped for 2.5 years. But Christopher Nolan had already told us, if Steven drops out, I may be interested. So we sat for 2.5 years waiting for Christopher Nolan to decide whether or not he was interested. Chris, by contrast with Steven, will not commit to a new movie project until a half a year after his last movie project comes out. He thinks about it for half a year and then makes a commitment. So in December 2012, he and his wife, Emma Thomas, who is always the lead producer on his movies, they made a decision, yes, they did want to do Interstellar. And he brought to this a strong science intuition, and he accepted my guidelines to the extent they do not get in the way of making a great movie. Now, he went into this with great trepidation. He was afraid I would play the science policeman, telling him what he could do and what he couldn't do. I went in with great trepidation. What do you mean, not in the way, so it doesn't get in the way of making a great movie? That means you're going to carry this off in some totally crazy direction, and it's going to be a mess. But we got together, and in the first hour of discussion, it became clear that we could work together very effectively, that we were on the same wavelength. And he brainstormed with me on the science in the movie through 3 more drafts of the screenplay. And the final screenplay and movie preserved Linda's and my science vision, but they changed completely the human story and the characters in major ways, because the Nolan brothers are superb storytellers, and they were much better able to craft a human story than we could. That means that Interstellar is truly the Nolan's movie, not Linda's and mine. However, the science in it, there's an unbelievably large amount of science in it, far more than you might imagine, and as I will indicate to you. And it's really a lot of really very interesting science. I think unlike in reality any other movie that's ever been made in the amount and depth of the building of the science into the movie. And I made a decision only at the time we were within about 9 months of the movie coming out. I decided I wanted to write this book, The Science of Interstellar, and Chris encouraged me because it seemed to me that if we had this companion book, we had by then a great film. They were pretty much finished with the filming. and they were in post-production at that point. And I was so enthusiastic about the film, the science in it, I thought that I could write a book that would inspire people and educate them about the science to go hand in hand with a movie, and so that's what this book did. We did not announce the existence of the book before it came out because Emma, Chris's wife, and the studio executives were scared that if it was known that there was a book about the science in this movie, it would immediately get labeled as a brainy movie and people would stay away thinking they weren't going to be able to understand it. And so the book came out simultaneous with the movie with no prior advertising about it. Now, some of the movie science is rather firm, and in the upper right-hand corner, I'll put an F for firm science, and some is speculative. I'll put an S for speculative science, and you'll understand the difference between them as I go along. Let's begin with the relativity of time, with a capital F up there. It's firm. Cooper says to his daughter, Murphy, when I'm in hypersleep or travel near the speed of light or I'm near a black hole, time will change for me. It will run more slowly. When I get back, we'll compare. We might even be the same age, you and me. Imagine that. And this does happen in the movie. So you get in the dialogue, you get the prediction of what's going to happen. That's often the case. If you really want to understand what's happening late in the movie, you go search on your 10th time through the movie, you go search at the beginning, early part of the movie, and you'll find some dialogue that explains something mysterious toward the end of the movie. Chris told me that he had this planet that was going to be very near the horizon of the black hole. It's called Miller's Planet, and 1 hour on Miller's Planet is supposed to be 7 years on Earth due to gravitational time dilation. And I said to him, that's not possible. It's just absolutely impossible. And by then he knew me. He said he knew that I would make an off-the-cuff remark and that sometimes I was wrong. So when he said, I said it's impossible, a factor of 60,000 time dilation, he said, go do a real calculation, Kip, and come back and tell me. So I went and did a real calculation. And if Miller's planet is just outside Gargantua's innermost stable circular orbit, the closest it could be without falling into the black hole, and Gargantua does not spin, then the time dilation is only about a factor of 2/3. Just a very modest time dilation. And this is sort of what I knew, that it was modest. However, if Gargantua spins really, 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 really fast, then this ISCO, innermost stable circular orbit, has moved much closer to the horizon, and I just work out an approximate formula. 1 minus A is the standard formula in physics for the ratio of the angular momentum of the black hole to the maximum possible angular momentum the black hole can have. 1 minus A is 3 root 3 over 16 times the time dilation factor cubed. And he wanted a factor of 60,000 for that time dilation factor. That says that the spin of the black hole of Gargantua is within 1 part in 10 to the 14 of the maximum possible spin. That's astrophysically implausible, but it is physically possible, but though implausible. And under the rules that we said sort of adopted, if it was physically possible, well, we would accept it. And that's what he wanted, and so that's what he got. Now, here is a lesson. I was trying to be sure that everything in here was physically possible, that there were no showstoppers. And I was not talking to any physicist colleagues. And when I don't talk to physicist colleagues, I occasionally miss the obvious. And I missed something. There's an accretion disk around Gargantua. Its temperature is set to be the same as the temperature of the sun, so it's emitting photons that are in the visible region. However, those photons falling onto the black hole, or falling onto Miller's planet, they go through such a huge gravitational potential drop that by the time they hit Miller's planet, they are hard X-rays. And it's kind of unpleasant for the humans to be down on Miller's planet with hard X-rays coming at them off the accretion disk. I don't confess this in the book, The Science of Interstellar, because I didn't notice, I didn't realize it until much later. And so that to me is the biggest embarrassment in the whole thing. And it is a lesson, and a lesson I want to give to all of the young people here. Go talk to your colleagues. Don't try to do things all by yourself, because your colleagues, they're likely to find your mistakes or help you find your mistakes, where you occasionally will make a big boo-boo, like I did. Okay. So the orbit of Miller's planet, it's helpful to just see what it looks like in an embedding diagram. So if I take an equatorial slice through Gargantua, and then I embed that in a flat space, so I just add one additional dimension. It's the fifth dimension in this movie, because you have east, west, north, south, up, down, three spatial dimensions. Then you have time as the fourth dimension. In this movie, there's one fifth dimension, which is the dimension of the bulk in which our universe lives. And our universe is warped by being shaped in a non-flat way inside the bulk. And that's what it looks like. It's a really, really long neck. And this is just putting in the numbers that come from the Kerr metric for a spinning black hole for this planet, and for the shape of space around the black hole. This is the orbit of the Endurance mother spacecraft, and this is the orbit of Miller's planet down here. And when they go from out of this, in the Ranger daughter spacecraft down to the Miller's planet, they come way down the throat of this black hole down to Miller's planet down there. This is the physical distance from Gargantua. It's still quite a ways from the horizon, but the circumference of the orbit is essentially the same as the circumference of the horizon, but it's way up here in the bulk away from the horizon. So that's quite interesting to see. And let me now talk about tidal gravity. I talked about this a little bit last night. Who here was not here last night? Okay, so there are a fair number of you. Okay, so tidal gravity is quite familiar to you. You have the moon. It raises tides on the Earth because the gravitational pull of the moon is greater on this side of the Earth than on that side. This arrow that indicates the gravitational acceleration of the moon is longer. And that means that that differential, it means that the ocean tide is raised on this side and it's sort of left behind on that side as the Earth falls freely. And there's a gravitational pull that has a slight inward component on the sides. And so you get the high tides toward the moon and the low tides on the sides when you ignore any effects of friction. If you think of it from the point of view of the Earth, and so you just go to a freely falling reference frame, then you just have the stretching and the squeezing. And the difference in the acceleration on the side toward the moon from the acceleration of gravity of the moon at the center of the Earth, that's the tidal force on this side of the planet. And that difference is the Newton's gravitational constant, the mass of the moon, divided by the radius of the orbit of the Earth, cubed, times the radius of the Earth itself. This is just from differentiating the inverse square law once and sticking in the separation between the center of the Earth and the surface of the Earth. And so I just want to identify this as the tidal gravitational field. And it just looks like the ordinary inverse the ordinary gravitational pull, but it's an inverse cubed law instead of inverse square, because it's describing the difference in acceleration between the center of the Earth and at the surface of the Earth. And so you'll just remember that. So for Gargantua, it's quite similar, but you have Gargantua here then, and you have Miller's planet there. This is the one that's very close to Gargantua. And Miller's planet, we choose the mass of Gargantua such that Miller's planet is noticeably deformed gravitationally for a reason that I will explain in just a few minutes. Okay, and so that gives rise, it turns out, and I'll be explaining why that's the case, to giant water waves that don't break.
How long for the engines, Case?
A minute or two.
Well, we don't have it. Come us on! Brand, co-pilot, you're up. Case, blow the cabin oxygen through the main thrusters. We're gonna spark it.
Roger that.
Lock! Depressurize. Engines up!
Now, why don't those water waves break? You see two of them, actually. One just not shortly after they land on this planet, this water wave comes by and it sweeps over them. And then another one, this is the one where they basically escape when the water wave comes by. But the water waves propagate along, maintaining their shape without breaking. Why? This is a rather interesting thing about water waves that you can have in two dimensions. So if it's a water wave that's very wide and rather thin, there is dispersion in the sense that the water feels the ground beneath it, and the long wavelengths travel faster than the short wavelengths. And so that would make the water wave come apart, with the long wavelengths traveling faster and the short wavelengths traveling slower. You also see this at the ocean. If you just go out and you look at little water waves just above the sand, the short wavelengths, they move a lot smaller, the short waves, than the longer waves. But then there's a nonlinearity effect that the higher part of the wave travels faster than the lower part of the wave. And that's what causes a wave normally to break. But if you have this wave that is wide and relatively thin, you can have the two effects balance each other beautifully, and the dispersion and the nonlinearity balance each other, and you wind up with a wave of a precise shape that runs along stably, governed by what is called the Korteweg-de Vries equation. So this is something that's well known to people who know about hydrodynamics, perhaps less well known to theoretical physicists like me. But the peak is about 5 times higher than the depth of the water for this. On the water planet, it's clear they're in water that is sort of waist high. So how can that be? Well, the answer is pretty obvious. They've landed on a submerged island, and this wave is coming in, and the submerged island is so small compared to the size of the wave hardly notices it, just comes in and sweeps over the submerged island over them. And so this is what's really going on. And in the movie, the wave steepness is exaggerated, but not by very much. If you look at this shape that I have here, which is the shape that comes from the Korteweg-de Vries equation, it is pretty close to the actual shape of the waves that you see in the movie. This is an example of the physics that's built into this movie that is very solid and rather interesting that many physicists are unaware of, some are aware of. So what makes this water wave? Well, let's return to Gargantua's tidal gravity. And first let me say, the deformation of Miller's planet, the key thing is that the tidal field, as I said, was g times the mass of Gargantua divided by distance to Gargantua cubed. And the distance, that's really the circumference of the orbit divided by 2 pi is what it is in warp space-time. And you put in these, basically, that circumference is g times the mass of Gargantua divided by the speed of light squared. That's half the Schwarzschild radius, which is the appropriate thing to put in. The tidal field then scales as 1 over the mass of Gargantua squared. The bigger Gargantua is, the weaker the tidal field. Small Gargantua, enormous tidal field. Big Gargantua, a weak tidal field. And so we adjust the mass of Gargantua so that the planet will be modestly deformed. And that means that the mass of the Gargantua is 10 to the 8 solar masses. Their horizon circumference is the same as the Earth's orbit. And so that's interesting. So you have a pretty darn big black hole. It's the size of the Earth's orbit. And it has a tidal field that will deform the planet, Miller's planet, but humans don't feel it. It turns out that that tidal field is basically the same as the tidal field that we have on Earth, that we live in every day. So it deforms big things, but it doesn't deform little things like us. How are these gravitational waves generated? Now here is the interesting story. Miller's planet has just been captured into that orbit a short time ago as seen on Miller's planet. It's a long time ago. Remember, a factor of 60,000 in time dilation. But a short time ago, it was captured into orbit. It has not yet settled down into orbit, and it's sitting there swinging back and forth under the gravitational pull of Gargantua, which is below it, just swinging back and forth. That's the way it goes. And you put in the number for the mass of Gargantua, you find that the swinging period is 1 hour, and the time between waves is 1 hour. And clearly, the swinging back and forth, the oceans on Miller's planet are sloshing back and forth under the gravitational pull as the planet swings. So everything hangs together perfectly, and that's the way it was designed to be. And over and over and over again, there's stuff hidden that you, as a physicist, you won't generally notice, but on your 10th time through the movie, you might notice a few things like this, or like gravitational slingshots that play a huge role, but you only hear the word a couple of or 3 times in the movie that is really part of the backstory and part of the firm backstory. I'm going to skip over this and this and move on to visualizing Gargantua and its disk. So I talked about this yesterday. For those who weren't there, I'll go through it quickly. Oh no, I didn't talk about this aspect. So the standard method of producing images for movies is that you have a camera, say a fictitious IMAX camera, and in this case, you imagine a light ray that begins at the upper back face of the disk and travels to the camera. It comes up over the black hole, and it gets pulled down by the black hole's huge gravity and comes to the camera like that. And there's an adjacent light ray that comes down to the adjacent pixel. So you think of little tiny pixels here. You've got 26 million pixels on an IMAX screen. And each pixel has its own light ray that comes off of the accretion disk if you're seeing a piece of the accretion disk. But if they're adjacent pixels, one of them comes off of here and the next one comes off of there, a long ways away. There's no way you're going to get smooth images or smooth videos. And there's no way, it turns out, you can even interpolate under those circumstances. So the standard way of making images and videos just does not work. So the solution to this was conceived by Oliver James, who was the chief scientist at Double Negative Visual Effects, or so-called DNEG in London. And he told me, he pointed out this problem he was having. He said, what we want to do is propagate overlapping light beams, Gaussian light beams that have Gaussian cross sections. But if you have overlapping light beams, then they're going to continue to overlap as you follow them from being little circles overlapping at the camera until they are very highly electrical light beams overlapping. And so we wrote a technical paper that we published in the journal Classical and Quantum Gravity that describes this technique of doing this and how it works. And this is widely used now in both Hollywood and by astrophysicists doing imaging around black holes. And so let me go on then. We made the disk an old cooling disk, not actually accreting, it's just cooling. There's no magnetic field or jets. The black body emission at 4,500 degrees Kelvin for human safety, marginally optically thick, and a painting of it was made by the artist Eugenie von Tunzelmann, and this gave rise to this image here that I'm showing to you. And Christopher Nolan looked at that and he said, it's going to be confusing for a general audience that this thing is so lopsided. I mean, what's going on here? It looks so different on that side from that side, which is due to okay. Can you hear me now? Okay, good. Yeah. So he said, for the purpose of making images of Gargantua, I want you to slow this spin down to 0.6 instead of that very, very high spin. And so we did that. So this is not known unless you read my book. And he said, don't put on any Doppler shifts because, and I explained last night in my lecture that the human eye cannot distinguish colors nor brightness levels from something that is as bright as this disk. And so you should make it like a human eye would see it. And so there's no Doppler shifts at all, and it's made much more symmetric, and this is the image that you wind up with. Okay, and so then we go through the story of why the black hole, why Gargantua looks like that. And the light ray goes up over the black hole down to the camera from above, and that makes the upper branch of the image in the lower left. And the light ray from the bottom back face of the disk makes the lower branch of the image, and the light ray from the front of the disk makes the crossbar of the image. And that is quite a contrast with the photograph of the black hole in the galaxy M87 as seen by the Event Horizon Telescope, as I discussed last night. And why different? And as I explained last night, Oliver James at Double Negative said, take the camera from the IMAX camera that is in the equatorial plane of Gargantua and just move it up to the North Pole and then smear things out because the astronomers have such poor resolution, and it looks more or less like what you see in the photograph of M87 made by the Event Horizon Telescope. So that all works out quite beautifully. But there is one extra factor, and that is that the gas around the black hole in M87 is moving in a three-dimensional way. It's not actually in a thin disk. That's why, actually, for the case of M87, you actually see some Doppler shift in the case of M87. It's bright on this side and dim on that side, even though you think of ourselves as looking down on the North Pole. In fact, it's a three-dimensional flow, and so even from this point of view, there is some Doppler shift there that the human eye wouldn't see if you were up really close to it, but when you're making photographs, it's seen. Let me just say that after this was all over, we sat down and said, we played with the computer program that my colleagues made at Double Negative, and we sped the black hole spin up to A equal 0.39, and then we put the camera in the equatorial plane. And then we looked at what happens as the camera goes around the black hole in orbit. You see all of these strange phenomena, which are all due to caustics in gravitational lenses. There's really interesting stuff going on here. You see images created from nothing in pairs. The two stars come apart, the two images come apart, and this one goes that way, and this one goes that way. This guy meets another image, and the two images annihilate and is gone. You see this creation and destruction of images in pairs that's all associated with what are called caustics of the passed light cone of the camera. And it is something that I was aware of, but I'd never really seen it up close. And with this new technique that we had devised for doing the building videos, we had the resolution to be able to see phenomena in gravitational lensing with caustics that are just fabulous to see and strange to see. And it's wonderful to use if you're studying in a course in optics and learning about caustics. I won't go into the detail. You go read our paper in Classical and Quantum Gravity, by far the most downloaded paper ever published in that journal. Okay, Interstellar's wormhole. There are severe problems with wormholes, as I said in my talk last night. I'll go through this very quickly. I did this last night. If you have a particle of light, a photon, trying to travel through a wormhole, then it gets caught as the wormhole pinches off before it can get through, and that leaves you with just two singularities. And so there's an issue of holding the wormhole open. How do you hold it open? You fill it with exotic matter, material that will repel gravitationally. And how do you get that? It's something that, more technically speaking, and now I'll get more technical than I was last night, this is due to Dennis Gannon, a relativist way back in 1975. In order to hold this wormhole open, it needs to be true that as you do an integral of the stress energy tensor associated with whatever may be inside the wormhole, the integral of the stress energy tensor through the wormhole, and this is an affine parameter, so-called, in the integral, and that integral has to be negative. And what that means, it turns out, this is a precise theorem, is that the average energy density as seen by someone who travels through the wormhole at almost the speed of light has to be negative. And this is a very precise and beautiful mathematical theorem that you can prove. And so then you go through trying to see if you can conceive of a way to build material in there that has a negative integral of this stress energy tensor integral integrated through the wormhole. And the only hope for doing this is through vacuum fluctuations, which I talked about last night. You have a box, you remove from it everything that can possibly be removed, and you're left with these vacuum fluctuations. Vacuum fluctuations are ubiquitous. I talked about them in cosmology last night. Let me talk about them in real life today. They are ubiquitous in real life. For example, they play a key role in the Big Bang birth of our universe. That's what I discussed last night. They play a key role in Hawking radiation, as I discussed last night. But if you just take a laser beam that's coming out of a laser pointer, I've got a laser pointer here, and if you just take that laser beam, the photons in that laser beam arrive in a random sort of way described by a Poisson distribution. And that turns out to be entirely due to a beating of completely steady light against vacuum fluctuations of the light. The vacuum fluctuations, the amplitude of the vacuum fluctuations beating against a completely steady amplitude made by the laser produces the shot noise with its random arrival. So just in ordinary, just sitting right here, we've got vacuum fluctuations visible if you actually look at the random arrival of the photons with their Poisson distribution. And then the key thing is that if these vacuum fluctuations are fluctuating all the time, and you can imagine a situation in which this region of space lends fluctuations to that region, the region that borrows the vacuum fluctuations winds up with a positive energy, and the reason that lens has negative energy after renormalization in the sense of quantum field theory. Quantum field theory, you have to do a renormalization on these vacuum fluctuations. Otherwise, you get basically infinite energies in them, 1/2 of a quantum per mode. And after renormalization, then the lending region winds up with negative energy and the borrowing region with positive energy. And so that's the foundation for all the really interesting gravitational phenomena associated with vacuum fluctuations, some of which that I talked about before. And that's the lending region is exotic, the borrowing region is not exotic. And so by manipulating vacuum fluctuations, this becomes the foundation for quantum precision technology, which I talked about last night. I will not talk about today. It's used crucially, for example, in LIGO today, which I talked about last night. And there's a question of whether or not you can hold a wormhole open with the aid of vacuum fluctuations, which I talked about last night. I'm going to skip over now and just move on. But the answer is maybe. We don't know. So let me move on and talk about Interstellar's wormhole after that. So the bottom line is we don't know whether or not it's possible for a very advanced civilization to construct a wormhole and then hold it open with exotic material which is made by some means of manipulating vacuum fluctuations. We don't know. My guess is the answer is no, but I've been proved wrong too often for me to urge you to believe me when I say probably not. And it's certainly been proved wrong often enough that I'm perfectly willing to make a movie in which you hold wormholes open with vacuum fluctuations, but it's an advanced civilization doing that. Okay, let me talk about Interstellar's wormhole. So for Interstellar, I constructed a 3-parameter metric for a wormhole. The metric that describes the shape of the wormhole has a lensing width. Basically, how wide is it by the time you get roughly the same distance up here is from the throat. When you go up to a point where this is going at a 45-degree angle in the embedding space or in the bulk, you have a lensing width, you have a length for the throat, and you have an actual radius for the throat. So just 3 parameters. And then my colleagues at Double Negative Visual Effects, they made an image of what it looks like when an IMAX camera looks through the wormhole, and images on the other side of the wormhole, paintings that describe what's going on in the center of this distant galaxy, the gargantuous neighborhood. Oliver James incorporated the equations I had given into their computer program and computed then what you got. And Eugenie von Tunzelmann, the leader of the artistic team, made the painting of what's going on in the core of this distant galaxy. After we propagated light through the wormhole to produce the images, the image that Christopher Nolan liked was this image. So he looked at the images of the black hole. You're looking into the wormhole, you're looking into the wormhole, and you're looking at light coming through from the other side. And he said, I really like the way this looks. So that's the wormhole we're going to use. I've chosen the shape for the wormhole based on that. And it turns out to be a very short wormhole with a small lensing length and a diameter of about 2 kilometers. So we discussed this in a paper we wrote for American Journal of Physics, in which, in this case, they're not strong tidal forces, so you can just build images through ray propagation. And so for undergraduates who want to do so, we've given you the equations where you can go build your own computer program, and you can build your own images of what's inside the wormhole, and you can change the shape of the wormhole, and you can see what it looks like as you change the shape of the wormhole. So then, having done this, Chris said, okay, now we're going to go through the wormhole. And you send to me, he said to the people at DNEG in London, you send me a movie of what it looks like to go through the wormhole that I chose. And so this is the movie that they sent. Let me begin by saying this wormhole is 2 kilometers in diameter. That's the planet Saturn. The wormhole this wormhole mouth is obviously far closer to us than Saturn is. That's why it looks like about the same size. And it's gravitationally lensing Saturn. So you have an image of Saturn distorted on this side. You have another image of Saturn highly distorted on that side due to gravitational lensing. And then in the interior, you're seeing into that distant galaxy 10 billion light years away. And now we're going to make the trip through this wormhole. So we're headed down toward the wormhole mouth, and it pushes Saturn to the side, the 2 images, because we're heading right into the wormhole. We won't see the 2 sides anymore. And we're now entering the mouth of the wormhole. We're traveling through. We're now out the other side. And at that point, Christopher Nolan telephoned me. And the whole movie has been shot. They're in post-production. And they're only then doing this imaging of what it's like to go through the wormhole. And he says, calls me up and he says, we got a problem. Come over. I came over and he showed this to me and he said, what do we do? And I said to him, you use artistic license. This is the only place where I said to him, you use artistic license. Obviously, you've got to deviate from what this does. And so this is what he did then. What you're going to see is the true trip. You're in the Endurance mothership. The mothership is going orbiting around the wormhole mouth. And then Cooper says, we're going to go through it. He pushes a joystick. And the ship heads on down and into the wormhole. And everything, until he pushes that joystick, everything is precisely correct. It follows the laws of physics. It's based on imaging using the computer program that Oliver James wrote based on the equations I gave him and the paintings by Eugenie von Tunzelmann. And well, let's see what happens. So this is the real thing.
Everybody ready to say goodbye to our solar system? To our galaxy? Here we go.
Artistic license that is based on combining various movies with various sizes and shapes of wormholes and then adding some sound effects. But it is the one place that I threw up my hand and we agreed we would deviate. Now, something that people are not generally aware of is that Christopher Nolan, in every science fiction movie that he has made, he has what he calls a rule set. And a rule set is a set of rules that constrain the action, constrain what happens in the movie. And these rules place very firm constraints on. He adopts them before he finishes the screenplay. They're built into the screenplay. And he doesn't deviate from them. And the audience, as the movie develops, sort of begins to get some sense there are constraints on what can happen. There has to be some rule set, and that gives the audience some confidence in the movie, and that it really does correspond in some sense to real life. And in fact, Christopher Nolan's rule set is something that corresponds to my laws of physics, my chosen laws of physics in the speculative region. And so here we are discussing this. And I proposed to him a specific mathematical model for the properties of our universe in the higher dimensional bulk, where it's now speculative stuff. We don't know whether there is a higher dimensional bulk. We don't know what goes on in this higher dimensional bulk, but there is a mathematical model that underlies this all. And so my contribution to his rule set was the mathematical model of our universe that then constrained all the action that could go on. It constrained everything in the filming from the outset before the filming ever started. And so let me tell you about the mathematical model of our universe in the bulk that underlies the entire movie and is central to the last third of the movie. So let's begin with the fifth dimension. We have our universe. It has its three space dimensions, east, west, north, south, up, down, its fourth time dimension, and then in the bulk there's an additional dimension goes out of our universe. The out-back dimension goes into the bulk. And in order to visualize that, I have removed the up-down dimension so that we see our universe as though it's two-dimensional with the up-down dimension removed, but you do see the out-back dimension. So that is just a way to be able to visualize things. And you just remember that our universe is this pink brain or membrane that has one dimension that has been suppressed. Now, the trouble with gravity in four space dimensions was what we have here, is that if we have a source such as the sun or the earth, and it has gravitational field lines in the sense of Newton, just an ordinary gravitational field line that goes out along the direction that gravity pulls. If you have a flat four space dimensions, well, gravity can spread into the bulk, just like it does in our brain. The bulk is no different than our brain. And so if you think about it, you wind up with an inverse cube law for gravity. And that's not acceptable. We know you've got an inverse square law for the gravitational pull. And so something has to be done to deal with that. And it was Lisa Randall and Raman Sundram who realized that there's a simple answer to that. You make our brain be embedded in five-dimensional anti-de Sitter space. And this is five-dimensional anti-de Sitter space, just like looks like a flat. This is the fifth dimension direction, dw squared. There's a compression in space-time of our four space-time dimensions, and a compression as you move out in the w direction, the fifth direction. The lateral dimensions all get compressed. So what this looks like is this, and this is Randall and Sundram. It is called braneworlds. It is the simplest version of braneworlds, but it's standard stuff that high-energy physicists work with and have some serious motivation to believe that something like this may actually be true. And so if I move directly upward out of our brain, or you move directly upward, and a friend of yours moves directly upward, and we go up by a distance of 0.1 millimeter with the parameters that I've chosen, then if our separation is 1 kilometer in our brain, then the separation a tenth of a millimeter up is 100 meters. Go up by another tenth of a millimeter, it's 10 meters. Go up another tenth of a millimeter, it's 1 meter. There's a very rapid shrinking of space laterally as you go up. And with that going on, then there's no space up in the bulk for the gravitational field lines to extend it into. There's just no room up there. And so on a scale of about a tenth of a millimeter, they bend over and they run along parallel to our brain. And you would get an inverse square law, except down at a scale of a tenth of a millimeter, you don't have an inverse square law, but beyond a scale of a tenth of a millimeter, you do have an inverse square law. So this is Randall Sundram. However, if we do that, then there's no room for us to have any adventures in the fifth dimension. So we can't go up into the fifth dimension and have five-dimensional fun. So we've got to do something beyond that. And so I had the idea, we'll put on a confining brain after we've gone up by 1.5 millimeters total. So there's been a factor of 15 E-foldings as you go up. Then there's a confining brain, and you have flat space-time outside here. And down there, you have flat space-time outside there. Then you get the inverse square law that you need. You have plenty of space up in here for adventures, and everything is just fine. So I sent a note about this and described the model that I was working with. I said, this is the model I want to use for Christopher Nolan's rule set in the movie Interstellar. And this is Lisa Randall at Harvard. And she phones me up. And she says, I've got good news for you, and I've got bad news. And I said, okay, let's hear the good news first, okay? And this is 2006. And so this is still quite early in the development of this movie. It's actually before Christopher Nolan comes on board, but we're still working with Steven Spielberg at this stage. The good news, this particular braneworlds mathematical model was proposed as a serious model for our universe and explored in the year 2000 by Ruth Gregory, Valery Rubikov, and Sergei Zibirikov. It's in the literature. You can go read all about it, and about all its properties and why it was really an interesting model and why people took it seriously. But the bad news is that then Ed Witten and others showed that this model is highly unstable. But the confining brains have a lot of pressure in them, and if you take a meter stick and you compress the meter stick, it will buckle. You just push and push, and there comes some point, if you put on enough stress, the meter stick will buckle, just bend up and break. And this is called buckling by engineers. And so you have the problem that this pressure in the confining brain is going to lead the confining brain to go crashing down and hit our brain, and you're going to destroy our universe. Okay, so there's a problem. Okay, so now let me move on. This is what we're beginning with. So this is the model that we adopted for the universe, and so somehow this has to be dealt with. Gravitational anomalies play a major role in the movie Interstellar. And so Cooper, for example, tosses a coin into the air, and every time, let me start over again. I talked about this yesterday, but there's a dust storm, the dust falls onto the floor in Cooper's home, but it falls in stripes, mysterious stripes. Cooper, trying to figure out what's going on with his daughter sitting here beside him, she's about 8 years old, he tosses a coin into the air, and that coin always lands on a dust stripe. And then he turns to his daughter and he says, I don't have that part of the film here, he turns to his daughter and he says, it's gravity. It's a gravitational anomaly. Gravity is actually pulling stronger onto the dust stripes locally than it is in between the dust stripes. And so Professor Brand and Murphy, 15 years later, are struggling to understand these anomalies. His daughter, Cooper's daughter, Murph, has grown up to be a physicist in her own right, and a theoretical physicist, and is working with Professor Brand to try to understand the anomalies. Why? In order to save humanity from a dying Earth, if you remember the movie. And why do they want to do that? It's in order that they be able to lift the remnants of human civilization, and most of human civilization has died, lift them up off of the Earth in big space colonies, despite not having very much rocket power. And so they have to turn down the Earth's gravitational pull in order to do that. They can do that by reducing the gravitational constant, G, near Earth for a few hours. Now that sounds like a crazy idea, but in fact, when I was a graduate student at Princeton, there was Bob Dickey And his former student, Karl Brans, had a theory of gravity called the Brans-Dicke theory, in which the gravitational constant was controllable by a scalar field that could be adjusted, and as it was adjusted, the gravitational constant would change. And so it seemed to me, well, why can't there be a field that lives in the bulk that controls the gravitational constant near Earth, and somehow that field controlling the gravitational constant then enables you to turn gravity down. And so all this crazy, seemingly crazy stuff about turning gravity down actually came from me before Christopher Nolan even joined the project. And so the details of that are told on 16 blackboards that sit on the professor's wall. The full mathematical details, you can go read those blackboards on my personal website and try to figure out the details. And these are the details of how Professor Brand and Murph are trying to figure out what is going on in the bulk, various bulk fields that are controlling the gravity, and that if they can learn how to access these bulk fields, they can manage to turn gravity down and for long enough to get humanity off the surface of the Earth. Murph at some point realizes that only half of the answer for how to do this is on the blackboard because there are too many fields. They have to have fields that live in the bulk that, one, stabilize the confining branes so they don't go smashing down and destroy our universe, and these fields have to be able to adjust gravity, and there has to be some way for humans to access these fields. So you have several fields that live in the bulk that are doing this for you, and you have several couplings, and you don't have enough data from the observations of the gravitational anomalies and the theory of braneworlds in this model of the universe, enough data to really pin down what's going on. So you needed more data, and she realizes the other half may be inside Gargantua. And the missing information, and there is something that she talks about, the professor's equation. The professor's equation is an equation for a classical limit of a quantum effective action. Now, this is something that the high-energy physicists will know about. Classical limit of a quantum effective action for the laws of physics in five-dimensional space-time. And in that quantum effective action, you have all these fields that are stabilizing the branes and that are controlling gravity. And if she can get a clear understanding of that classical limit of the quantum effective action, then she's in, and she'll know how to control gravity. And so that's the backstory. Chris Nolan and I then worked together very hard to get the remainder of the story to fall together. And I'm coming to the end of my talk now. And he, as I said last night, Chris wanted an ending that is more mysterious than the ending of the movie 2001: A Space Odyssey, Stanley Kubrick's masterpiece. And so he got it. I helped him get it. And it all deals with what's going on in the backstory on those blackboards. So that's where physicists can go in, and who knows braneworlds and knows about quantum effective actions, go in and see my attempt to provide the professor with the tools that he needs. And where would they learn the quantum effective action, which is the missing pieces of information? From a singularity inside Gargantua. And so I discussed last night the fact that there are several different singularities inside a black hole, and this is modern general relativity research has told us this with pretty high confidence, though we need computer simulations of the interior of a black hole in order to be absolutely sure that this is what goes on. And the key issue is that although the horizon of a black hole is highly stable, You perturb it, it vibrates and settles right back down. The interior of a black hole is highly unstable. And you're told what goes on with the Kerr metric, that there are inner horizons and that there is a ring singularity. All that is unstable. And the moment stuff falls into the black hole, the whole character of the interior of the black hole changes. And so that is a whole major area of relativity research that has been going on since about 1990, beginning with Werner Israel and Patrick Brady. Werner Israel and Eric Poisson, who was his student in Canada back around 1990. That has been largely sorted out, but not with complete competence. So there's a chaotic singularity down at the center. There's so-called infalling singularity and an outflying singularity. And I went into that last night. I won't go into it again. But the outflying singularity, I'll just tell you, that is created by everything that fell into the black hole before Cooper falls into the black hole. It gets a little bit scattered back and piles up in a very thin layer, sort of a shock singularity. That's a singularity that is governed by the laws of quantum gravity and yet is gentle enough that Cooper might be able to survive it if he encounters it. And so Cooper is told by his daughter, if you can go inside the black hole and get me information about about quantum gravity in the vicinity of a singularity there, that might enable me to get the last piece of information that I need in order to learn how to control gravity and turn down the gravitational pull of the Earth and enable humanity to be saved. So here's
Forcing the event horizon. Port side, dipping down beneath it. To go through it.
So he's gone through the horizon. You look back and you see the external universe above him and the ring of fire due to the accretion disk around the black hole. And he keeps going on in. And he approaches this outflying singularity that Romilly, the theoretical physicist that's on the expedition with Cooper, has called a gentle singularity, because it's the most gentle of the three singularities. Just before they reach the outflying singularity, the Ranger spacecraft that Cooper is riding in gets torn apart by tidal gravity, but he doesn't get torn apart. Remember, the bigger an object is, the easier it is to tear it apart. The worse the tidal forces are on it. So he is ejected from that, and he goes flying down in his space chute toward the singularity, as does Tars, a robot who made the trip with him. And Tars collects the quantum gravity information there and is ready to send it back if they find any way to do so, ready to send it back to Murph. But of course, they don't know whether they're going to be able to get out of there or not, but at least they've got the quantum gravity information. As Cooper falls in, he is captured just before he hits the singularity by a tesseract. And this tesseract is a spacecraft that lives in the fifth dimension. It lives in the bulk. It has four-dimensional faces. And these it has three-dimensional faces. It's a four-dimensional cube with three-dimensional faces. And he is captured into one of the three-dimensional faces of this four-dimensional cube. And so he is all the time living in three dimensions. And initially, this three-dimensional face coincides with our brain, and he's captured into it. And then the tesseract lifts him out. Okay. Let's see. Hello, can you hear me? Okay. I'm essentially finished, almost finished. This is him being captured by the tesseract. So he's captured by the tesseract, And he's now inside the tesseract. The tesseract lifts him up and carries him across the bulk, this short distance back to Earth. Remember, it's 10 billion light years in the brain, but up above in the bulk, it's less than the distance between the Earth and the Sun. And so the tesseract can travel rapidly, and in just a few minutes, he's carried back to Earth. And what is he doing while that's going on? He's kicking and screaming and twisting and just totally disoriented. And you see scenes like this, but you are not told at the time that, you're not told that he got captured by a tesseract that is a spacecraft that lives in 4 dimensions, in 4-dimensional space that goes up into the bulk and carries him back. You're not told that at all, and there's no way you're going to figure it out until you read my book or you've seen, or you have watched the movie 10 or 15 or 20 times. The tesseract goes back, it docks beside Murph's bedroom, and all of the rest of the action that you see is with the tesseract docked there beside Earth's bedroom. And I'm not going to stop at that point. I think I've sort of run out of time, but just tell you that there is just such an enormous amount of science in this film that is tied to a very concrete mathematical model for our universe. It is the mathematical model underlying Christopher Nolan's real set for the movie. And it was enormous fun working with Christopher Nolan on it and building all of this science into it. And so let me go at that, and I'll answer questions.
Thank you very much, Kip. I think I know what I'll be doing tonight. Any questions? Take a couple.
We have time for a few.
Time.
Yep.
Yeah, thank you. In your opinion, is there an explanation for the value of the gravitational constant, even if we don't know what it is?
I don't have any wisdom about that at all. It's not something I've thought about. I'm not, you have to think, I think the only things that are really meaningful are dimensionless constants, if you think about it deeply. And so the issue, is there any explanation for the value of the Planck length that you build out of the gravitation constant, Planck's constant in the speed of light? And so I think that's the deeper question. I've not thought much about it, but that's the question I would prefer to be asking.
Mm-hmm. Yeah.
Was the wormhole and gargantua simulated in the 4+1 spacetime or the 3+1?
I'm sorry, were the wormhole and gargantua simulated in what?
In the 4+1 framework of the random syndrome theory or the regular GR?
So they were simulated in the model universe of Gregory Rubikov and Zibirikov, where you have this exceedingly thin anti-de Sitter layer, and you don't see anything in the movie that gives you any information about the structure of that layer. So it's basically as though you have our brain, and then you have a sort of disconnection, a discontinuous connection to the bulk, which has transverse dimensions enormously shortened compared to in the bulk. But the fanciness of the anti-de Sitter space and of that layer is beyond what occurs in those simulations, because they don't get down onto that kind of a scale.
Maybe one more question? Yes? Hold on.
So if the tesseract docks by Murph's bedroom, is the idea that he could be seeing into the past, that he was seeing into the past, is that purely cinematic, or was it kind of a relativistic idea as well?
Let me show you just a tiny bit more of my talk. just to get to that, okay. So we're going to skip over this. So here is Cooper inside the tesseract. The tesseract has a very complex structure, but it is this is what you see in the movie. I don't need to go into the details of that, but Cooper can see into Murph's bedroom. Let me back up, and better yet, let me back up. Let me back up just a. So here's Cooper in one face of the tesseract. Here's his daughter in his daughter's bedroom in the other face. And this is a four-dimensional cube as seen in 2 dimensions. If you think about this, this is what a tesseract really looks like. You go onto the web and you can understand this kind of a picture. And so he can see his daughter by looking up on a light ray that goes up through this face of the tesseract, and then through that face, and then down on her head. And that's one path for light rays. Actually, the light ray he sees comes off of her head and goes to his eyes. So this is his eyes looking at the top of her head. If he looks at the side, he sees her along a light ray that travels through his face, through that side face, and hits her over there. Similarly, this face, every direction he looks, up, down, east, west, all directions he looks, he sees his daughter. And so that's the character of a tesseract, where she is in one face and her bedroom is in one face and our brain is in one face. And he's in the other face, out in the bulk, but in a three-dimensional face. And so here you see, he can see into her bedroom through the back of her bookcase, here, there, all around him, whichever direction he looks, he can see her. So he then communicates with her back in time, because she's young, but he has gone through a process where she has aged, and she, in fact, by that time, she is a very old woman, basically. But he communicates with her, sending signals backward in time. And he does it by pushing on something that Christopher Nolan calls an extrusion. He sends the signals back to her. Now I have a space-time diagram, okay? And the interior of this is the bulk inside the tesseract. This is what Cooper's face of the tesseract is here. Again, you're just seeing Cooper's face as though it were a two-dimensional face. It's really a three-dimensional face. Here's the intermediate face, and there's her face, her bedroom. And this is the interior of the tesseract. And in the interior, in the bulk interior, the four-dimensional interior of the tesseract, there are closed time-like curves. Backward time travel is possible. And so here he is up here. Here's bedroom time, her bedroom time. This is Cooper's time. They're all living in 3 dimensions. So he pushes on the extrusions in a gravitational signal. Gravity can travel into the bulk, but other forces don't travel into the bulk. And so the gravitational signal goes into the bulk and starts winding along the edge of a light cone. So think of it as a gravitational wave signal, if you wish, running along the edge of the light cone. If you look at the light cone structure in the bulk, it winds its way down in the bulk, and then it winds up meeting Murph in Murph's past. So there is a time machine. There are closed time-like curves in the four-dimensional interior of the tesseract, but not anywhere else. Cooper never goes backward in time. Only the signals that he sends to his Murph go backward in time.
Right.
And again, this is in my book.
Well, I just wanted to say that it's not uncommon in science fiction or superhero movies that they create like the set of rules,
Yes.
like for Star Wars or the Marvel universe. And these set of rules are frequently called like the Bible for this universe. I want to thank you. We don't often have colloquia for someone who co-wrote the Bible. So, thank you very much.
Thank you.